Good morning. How are you? Okay, it's really foggy this morning. Start to clear up. Did you pass around? So again, Monday morning. I'll send out the next file by email sometime today. So that's what we're gonna do. I just gave you the homework number 3. This is very simple problem. Answer all is in the book, but you don't have to look up the book. I have a reason to give this particular problem. I convert everything, as I mentioned to you at the beginning of the semester, more design-oriented problem that you can think. This problem, some of you, some of you major in chemical engineering or chemistry. Not Songtae, not you, maybe. So you all have a basic mechanics knowledge, right? Everybody has strength of material. Anybody else, whoever doesn't have a background, just let me know. Because this course does not, chemistry. Chemical engineering, no problem. You, in sophomore, I think everyone should have a strength of material course, no? No? Well, yes, you're working together, then yes, you can help him up a basic, how to compute the moment, you know? So all that sort of the things. And you will return the first bi-weekly project today, right? And that project is not a heavy project at all. That's really to develop or fit the probability model to the actual data. That's what you are really looking into it. And the question is how to develop the probability model. That's all I want to say. You know, maybe different way of doing it. And after you return that project today, this morning, then I'm going to really review it. Then this Friday, I want you to present, okay? So each group, we have a 4 group, right? Four groups, 3, 3, 3, 2. Then not more than 10 minutes per group. So not only, the reason is not only really you present the project material with understandable fashion. You follow me, right? In English, of course. Then develop your presentation skill. I know all of you are doing really well for presentation skill. Do you know who are the best person in the world to present the PowerPoint fashion? Do you know? I start to hear the voice. Songtae? Steve Jobs is the best person for really PowerPoint presentation. That's one of the best success in his life. As I look at Steve Jobs special last night, 8 o'clock in KBS 1. Anybody saw it? He spent more than 10 hours for 1 hour presentation. So I look back myself to present 1 hour. Usually conference, they have a 20 minutes presentation, and keynote speech has about 1 hour. To prepare 1 hour presentation, I don't invest 10 hours. But what that means is there is things that delivers to the people in understanding fashion and a very effective fashion. So I want to also think about that too, okay? And this homework, when I give you homework today, when is the due date? When is the due date? Speak up. When? Tomorrow? Next week? Friday next week? No, Monday, 1 week. And if it takes longer, I usually assign more than 1 week or 2 weeks and whatever. This homework problem. This is a simple beam, and you have a loading P. And this is 5 meters. And of course, then a maximum bending moments occurs right at the middle. What's the bending moment? Expressed as a P. What's the bending moment expressed as a P? 중간. Well, let's say this is L. Bending moment. Let's say bending moments. So over here, the reaction force, this is high school mechanics, P over 2. Bending moments right here is half of the P multiplied by half of the L, right? So bending moments, critical bending moments is PL over 4. I'm going to call this as a resistance. Doesn't matter. I'm going to call this as resistance. I'm sorry, not the resistance. The S. We use R and S, okay? Then now, to make a probabilistic model, I have to think about the P as a random variable. So as you see in the homework, for the random variable, mu P is equal to 3 kilonewton. What's mu P? Who cares? Monday morning. Mu P is the mean value of the loading, okay? And sigma P is equal to, there's a standard deviation spread of the loading. If it's a deterministic, it's just 1 point, 1 constant. The sigma P square is equal to 1 kilonewton square. So this is going to be the variance of the loading. And So now I have to give a strength for the beam. So I'm going to say that the mean strength of the beam is 10 kilonewton meter. So this is a force times the length, that's a moment. So I'm giving you as a moment to make it easy, not the full design problem, partial design problem to check out how to handle the actual problem. And instead, I can give you sigma r square, but right here, I'll give a CV, COV, coefficient of variation, is equal to 0.15. This is the usual, the input, or from a vendor's sheet, you could have this easily as a part of the spec. So coefficient of variation is equal to mu r and sigma r, right? And this is equal to 0.15, take a, I'm sorry, you don't have to. This is coefficient of variation is sigma r over mu r, so that's what it is, right? Then you can compute the sigma r. And then assume, I said assume first the normal distribution for loading and the strength, bending strength, okay? Assume normal distribution. First problem, both are normal distribution. Very standard. From then, ask you compute the PF. If you compute the PF, you will compute the PF. The answer is 10 to the minus 4. Instructor so generous, because my purpose is not to see. You will do 100%. You will compute this correctly. But if you, at the beginning, if you write the wrong answer, then you can proceed the next step. So I really want you to prove the probability of the failure of the system is 7 times 10 to the minus 4th, okay? Confirm that. Normal distribution. That's what happened for most product. Then question is, as you compute, you have that, but your target PF, or you can call the design PF, is not this, but it is 1 times 10 to the minus 5th. Then now, in your position, what you're going to do? How the simple design you can change that it can meet the target probability of the failure. Very simple probabilistic design concept, okay? Clear, right? Question clear? Is it clear? And the second question I have here is, I think I gave a both, right? Not the both. Second problem, I said loading Loading is concerned log normal distribution. And resistance, bending strength is normal. Do we have a question? Talk? Loading is log normal, and the strength, bending strength is a normal distribution. Then what's the PF? Jinggyun, question? Talk?
We had some question about problem number 1.
Okay, go ahead.
If we calculate the PF, we can get 7.5 minus 4. So we have to...
You have to conform. I gave you the value. Could be wrong. Okay? Could be wrong, but that's what I expect. 7 times 10 to the minus 40 power.
So we have to reduce the PF, right?
You have to reduce the PF. Then what you want to do?
10 to minus 50.
Yeah. That's a target probability of the failure. Then actually when you compute that, that's 7 times 10 to the minus 4. Usual criteria is all around there, but I want to make sure that probability of the survivor is higher. So I can make a target probability of the failure is 10 to the minus 6 or 7. Then what do you have to do? Then starting from today or possibly Wednesday, I start to inject the safety factor. Then how you relate the safety factor with the reliability or failure probability. That's the whole idea. Okay, this is interesting. I gave some thought last night, then I said, let's do it, okay? Okay, another announcement is, I think this month sometime, I have to do some midterm exam. It's week of 8th, I'm going to give you week of 8th. This is a week of 5th. Still, I want to finish next 3 weeks. But Friday afternoon, you are usually off. You don't have any class, right? Do you have a class Friday, like 1 o'clock for 2 hours? Friday, usually you don't have a class, that's what I know. So I like to give you something like a 2-hour exam. So Friday 1 to 3, I feel is desirable. But if you can make it, then we have to go like evening hour, which is not desirable. So plan for that. Something like 1 to 3 or 2 to 4. Okay, that's what we're gonna do. Okay. Some corrections maybe we're gonna make because last Friday I confused a little bit about exponential probabilistic model for time to failure and the Weibull model for time to failure. But if you look at, you have my handout. Your handout was okay, right? All the notations, I use a math type, so-called. Then I'm pretty sure I converted it to a PDF file, then you got the PDF file. So if you look at page 5-3, you will see the Weibull distribution there. If you look at the Weibull distribution, I pick up the best features from a few different books and some papers, and they use a different notation, and that's what a little bit confusion on notation occurs. If you look at the Weibull distribution, FT in page 2, there is something like this. 1 minus exp minus t over beta alpha. And of course, t is greater equal to 0. That's what you will see there. Two parameters involved, alpha and beta. This is page 2. And of course, for the reliability is concerned, which is 1 minus ft t, because this really means, this is probability distribution model or cumulative distribution model. This is equivalent to say t is less than equal to t, then reliability is concerned is a complement to this, which is 1 minus ft. So you have reliability model is concerned is minus t over beta alpha. This is what is said exactly there. This is correct. There's nothing wrong on this one. This is all correct. But if you then on page 5-5, okay, this is one point, confusion point on Friday. Okay. Friday, page 5-5. This 5 is really nothing to do with a chapter 5 or if this is chapter 1. I just happened to randomly assign this number, so you don't have to much worry about it. And in the exponential model, here, this is Weibull, okay? For the exponential model, well, what would it be? What do you have to change from the Weibull function to get the exponential function? Alpha is equal to 1. So exponential model is like a special case of Weibull distribution function. There is no change. In that sense, we can just go ahead to page 5. So exponential function, or let's say this is Weibull, so I'm going to say Weibull. Same. And ft t is equal to 1 minus exp minus t over theta alpha. And t is this. What's the difference? I use that notation, the beta there, over here. Here in page 5, I happen to use the theta. That's the only difference. So don't confuse. Then I made corrections to my note, everything. I switched to theta. And I add a couple more pages for that section. Then I'm gonna send out to Higyu, and Higyu will send out to all of you. The exponential function, of course. So this is Ft, reliability is concerned, RT, T is equal to exponential minus T over theta alpha so no difference, okay, identical. Confusion is the worst enemy in the learning process. I feel better not to know it rather than confusing. Okay, that was a correction. And for the normal distribution for this particular homework problem, to compute the probability of the failure, both are the normal, then we defined safety margin as R minus S. R, resistance in generally speaking. S is like the stress or applied stress or applied loading. But when you really solve the problem, the unit has to be, unit of R and S have to be the same unit. You can't deal with a different unit. So this is a safety margin. That's what we did. And as I slowly introduce the safety concept, safety factor concept, and cast the implication to the reliability of the system or component, then what is the safety factor usually? Safety factor, or people use N, N1, N2, N3, N, but who cares? Whatever the symbol we use, you can really sort them out nicely. Is typical is R over S in general, okay? Resistance over the applied. That's what usual definition for safety factor. And the probability of the failure, then you can define probability of the failure is probability such that R is less than equal to S. Both, of course, here is random variable. Then we assumed last Friday, let's say both are the normal distribution. And you come up as phi m minus beta. You remember? Who cares? So then what's the beta? Beta is called reliability index. Beta is reliability index, and this happens to be the inverse of coefficient of variation. Coefficient of variation, as we indicated here is non-dimensional dispersion, measure of non-dimensional dispersion of the probability model. So like a sigma over mean. So this is mean over sigma in general. Generally, okay. In this case, this is by margin. So model the safety margin. So I can say this is that. Is that. And you should to generalize, whole idea is to get the probability of the failure. I'll write another 20 or 30 times the PF is equal to, in the my note, I just use PROB as a P, that's same as probability, R minus S, and for the two-dimensional, when you deal with the simple, the R random variable and S random variable, that's a two-dimensional. Then you can see if I draw the here, I can say, okay, this is R-axis and this is S-axis, and the probability zero, this is really nothing but the integrations of F, R, S, joint probability, of course, joint probability, two random variable that produce a joint probability function. If it's a 3, that's a fourth dimensional, but here I can say, okay, this is FRS, okay, and this is R. I'm going to write this way, and as I put in the note, and this is a joint. I'll just draw, you know, makes sense. The volume, I have to draw the volume. My graphics is so lousy. I brought some nice graph here. It's in your It's in your notes. Something like this. Make sense? This is I put the FRS. This is a probability density function for R and S. Joint probability density function is in your notes. So if you put some this. And this is R, and this is S. Do you see all that there, Arlene? It's in your note, page 11 or page 10. And this is a projection. This is a projection of the probability density function in the R-S plane. Okay, this is R-S plane. This is R. I reverse it. This should be R, and this should be S, because it's a right-hand rule. And here, this surface here, this surface projection down on the RS plane, and this is the line, RS plane is cutting plane, which is really so-called limit state, the value, or surface, depend on the, in this case, it's really line, okay? How come this goes all the way up just like that? So this is like, this is the plane. R minus S less than or equal to 0 is the domain to compute the probability of the failure. Probability of the failure is the volume of this R, S, and FRS. The density function is a volume, but R minus S less than or equal to 0 is the volume contained in the hatched portion, which is less than or equal. The other side is what? Complement of this is reliability rather than probability of the failure. Probability of survival, that's what the reliability is, which is in the other, the volume. Or you can subtract 1, you can subtract this shaded volume from the 1. And usually this volume, shaded volume, which is probability of the failure, is very small. So in the computation, sometimes it generates the problem. So you have to looking into that. That we will deal sometime early November. That time we will get into the multidimensional. You follow here? This is simple projection right on the RS plane. Okay. So now a little bit generalize it out of this, then this portion R can be generally collection of random variable x1. x1 could have a set as more random variable. Something like a material property you can deal as random variable, like a Young's modulus. All the structure relevant property you can put that in the x1, okay? And the length is also same. Thickness of the shell you can treat as a random variable. So lots of things you can think of. As a design parameters, you can say yield stresses, or ultimate tensile stresses, you can deal with the random variable, and S, any random variable related to the loading in the system, you can put that in the random variable. In that, the homework problem, you have only one loading P. You can have a multiple loading. You can have a pressure, which you can treat as a random variable. So in general, you can say, I can deal with a general function G as a collection of the random variables. Let's say X. And here G is called limit state function. So I can rewrite this guy up there in general. PF is equal to the probability, and G X is less than equal to 0. To generalize it. Okay. And integration form is concerned, F, and this is really the collection of the random variable X. I'm going to say that which is really X1, X2, all the way through Xn. Then here is dx1 all the way through dxn, and where in the domain gx less than equal to 0. Awfully difficult to solve. Then easiest tool, which you may not have, some of you may have, some of you who may not have knowledge on structure optimization, to optimize it by assigning the objective function, then all the side constraint. This is all the side constraint, then solve that integration. But problem, not the problem, thought was you are all working on the structure reliability, then suddenly you have to go study for structure optimization, then come back, which is not quite desirable. That's what the first order reliability method, which is really directly involved in solving this equation. Okay? That's what I'm going that direction. In the choice textbook, I really like it for about 1/3 from the beginning. It has a merit in there. Examples are really set up nicely. But suddenly going into the optimization, then you get lost. Because lots of terminologies are new, because pick out from the optimization, the techniques. So anyway, this is a very general expression. And this is what the failure domain is. Some people use this as a D, but it's all same thing. Less than equal. And limit state G, if Gx continuation of this, if less than equal to 0, this is a failure state of failure. And if G is greater than 0, which is a state of safe. And another region is G, X is equal to 0, which is a failure surface. So what that means is really failure surface. By looking at same thing you have in your note. So failure, this is a state of the failure for shaded. And the cut, which is really generated surface, it's just a cut. That's a failure surface. And all the other portion, all white here, this is a state of safe. Reliability is concerned, the volume of this, the white area. This shaded and unshaded, if you add the two together, which is the total volume of the probability density function, that has to be equal to 1, okay? So the probability of the failure I assigned as a homework, I said PF is 7 times 10 to the minus 4, small. That's why this area has to be, the volume has to be the very small. Okay, I feel more comfortable today than Friday, because when I start to screw up, I'll screw up forever. Is it clear? Should be clear. Then I ask a question to answer myself. Clear? Clear. Okay. So now special case out of this, because over here everything is assumed, all the random variable here can be correlated. But life is concerned, of course, is correlated in some degree, but usually lots of cases is independent each other. Each random variable, if all the random variables are independent, statistically independent each other, then everything is all simple. As example, I always use human relations. To make a decision when you're a bachelor alone, it's simple. Whether, well, I want to go this Saturday, I want to go trip myself to Tongyang. All I have to do is get up in the morning and eat and take off. But when you have a marriage state, it's different. When you get up in the morning, you can't just go. You have to ask your wife and husband, make sure they agree. But when you have children, what happens? Situation is a lot harder. Wife said, okay, let's go, it's going to be a fun. But children said, no, mom, I want to go Seoul Daegongwon, you know, it's amusement park I want to go. Then you have to scrap going down to Tongyang. You have to follow your children. So it is all constrained. So this situation is the bachelor state, right? If in this case it's with many children, but for the uncorrelated situation, when I say uncorrelated, which is the same as independent. When I teach the random vibration next spring, that's really probabilistic design. That's a dynamics. We use more uncorrelated rather than independent, but it's all the statistically uncorrelated. That's what that means here. Everything's all individual. So if I rewrite this guy, I just use one integral, but it's really you have, this is multiple number of integration. I can write this if independent. You know what I mean? Independent situation. PF can be integration, multiple number of integration for x1 domain all the way through xn domain, f x1 I can write this way, f x1 dx1 is all fx2 you can split everything as independent bachelor, okay, then multiplications. Much easier. Much easier. Then in the class we are dealing with R and S, which you can put in the 3D space with the probability density function. Then I can write this guy as I don't know how many times I write this. I can write this guy as integration R minus S less than equal to 0 f r s dr ds. This is last time to capture the essence of the probability of the failure expression for the independent situation. So I'm going to say assumption here is R and S are independent. Then I can write this independent, then R and S I can write this expression as multiplication. This is minus infinity to infinity. And this I can write here as domain is R is less than or equal to S. Then I can associate that expression as minus infinity to infinity. Then first integration is this, less than equal to 0 is the same thing, and FR dr, then Fs s ds, and this expression is FR s, okay? Then the whole thing I can turn to this as minus infinity to infinity, FR S, and this guy is just carries over ds, but S is integration parameter. Usually you can write as minus infinity to infinity, FR x, Fs x dx. This is only good when the random variables are independent each other. This is only good for all the random variables are independent each other. So this is, I felt, the simplest way to derive the expression this, but if you look at my note, I use the event A, event B, then probability A and B, then take an intersection, which is a really a slightly different way to get the same conclusion. Okay, I'll stop right here, and I'll see you Wednesday.